I am Pushpita Chandra. I am a PhD student at IIT Delhi under IIT Delhi and Ecuador exchange program. So I'm TA for this course, Applied Optics. So let's start the class. Today we will discuss some new topic which is called diffraction. Of light. So, what is basically diffraction? So, when a light from a narrow linear slit is incident on the sharp edge of an obstacle, it will be found that there is illumination to some extent within the geometrical shadow of the obstacle. This shows that the light can be bent around an obstacle. This kind of phenomena, like this, which are produced when the incident wavefront is somehow limited, are called diffraction of light. So, basically, that there is when Kind of. So this phenomenon cannot be explained by ray optics. Only wave optics can explain this phenomenon. And to describe this phenomenon, we need Huygens phenomenon. Cannot describe this phenomenon called diffraction. So Huygens theory or principle state that every unobstructed point of a wavefront at a given instant serves as the source of spherical secondary wavelets. The amplitude of the optical fields at any point beyond is the superposition of all these wavelets. So this is combined of Huygens and Friend's principle, and this principle is the key factor to describe diffraction. And diffraction, there are two types of diffraction. We know Fresnel's diffraction and Fraunhofer diffraction. Diffraction and Fresnel diffraction. So the key difference between them is that in Fresnel diffraction, the source and the screen both are at finite distance, and for Fraunhofer, both the source and screen both are at infinity. And how we do that? By infinity, we mean the plane wave is falling on the slit, and after the screen. But in Fraunhofer Fresnel diffraction, the wave fronts are not plane. So the commonly used diffraction we use in laboratory is basically Fraunhofer diffraction. It is used commonly in laboratory in optical experiment for its mathematical simplicity and well-defined patterns. But Fresnel diffraction, and also professor has have shown the difference in pattern in Fresnel's and Fraunhofer diffraction. So I'm not showing it. So at Fresnel's diffraction, it is important that optical phenomena where source and the screen proximity affects the observed phenomenon. So Fresnel's is actually near field imaging. So basically in front of a diffraction, sorry, it has been. This is Fresnel and this is Fraunhofer. So in Fraunhofer, a diffraction incoming and outgoing waves are plane waves, basically. And for Fresnel, the waves are spherical or cylindrical, mostly. Not mostly, like all the time, they are spherical or cylindrical. And you know that to make the rays parallel or plane wave, we need a lens, which is basically used in front of a diffraction, but no lenses are required in Fresnel diffraction. And the observed in Fresnel can make this difference. The comparison between Fresnel and Fraunhofer. Fresnel diffraction. This is the comparison between them. The source and screen at finite distance. At infinite distance. Then comes wavefront type. So as the source and screen are the infinite, the wavefront are basically plane wavefront. But here at Fresnel diffraction, they are basically spherical or cylindrical or mixture of them, depending on the example. So analysis, they have a more complex analysis. And diffraction pattern changes with the distance between source and screen, between the slit and screen basically. Simple analysis, and it is very much simpler and it doesn't change rapidly. And in final description, why the analysis is complex, because there is you need to consider varying path reference phase shift from different parts of wavefront, making the analysis more involved. Lenses, or your named lens here, do not need lenses. And what is the fringes? They are almost like straight or parallel fringes. They are carved. Carved means they have circular zone. So you will see that how can I write there we get straight fringes when you have seen that single slit. For single slit diffraction, the fringes are like this, all those things. So this is like this. The intensity changes here, but this, so this is a band, this is a band, this is a band. You will get on a screen a band like on this maxima, and this is the dark band here. So that's the reason I have written the fringes are basically straight here, but else we get like this kind of wavelengths. And okay, that is far field. This is near field refraction. Is Fraunhofer or Fraunhofer diffraction R should be b squared by lambda. Here R is the distance of screen. Equation. Okay. For Fresnel's, R needs to be less than b squared by lambda. So that's the mathematical approach. A simple yet logical bridge between the studies of interference and diffraction is the study of the linear array of n coherent point oscillators or radiating antenna, which are basically identical even to their polarization. So, professor has described this phenomena in the class very well. So, I'm going to write the last expression because the like mathematical calculation has also been shown. And these oscillators are identical even to their polarization. So we know that its expression is basically I is equal to I naught sine square n delta by 2 by sine square delta by 2. And here delta is basically kd sine theta. D is the distance between the oscillators. So the upper term varies rapidly, but this term doesn't vary very rapidly as it is very slow. So for this term, we get the combination of these two terms gives rise to series of sharp principal peaks separated by a secondary maximum. The principal maximum occurs when delta is equal to 2 and 5. So when m is equal to 0, plus minus 1, plus minus 2, plus minus 3, d sine theta m became invariant, and sine square n delta by 2 by sine square delta by 2 becomes delta square, for delta is equal to 2 and pi. This is the principal maximum. Now from this expression we have described single slit diffraction and how we can make a bridge between them that has been discussed in the class. Now, we know for single slit diffraction there are calculation involved, and there you need to like do a graphical solution, which is basically to get a maxima. That is, you need to equate theta is equal to tan theta. You will get the maxima condition and all those things. So basically for single slit diffraction, I theta is equal to I naught sine beta by beta whole square. This is single slit diffraction intensity relation. Here beta is pi d by lambda sine theta. D is the distance between them. So basically to match the diffraction to any coherent oscillator. So we assume that there are the coherent oscillators at a fixed distance, and we assume here that the slit, the upper point and lower point, we will like consider only these 2 points, and we will see the diffraction pattern as if or there if the oscillators are at that distance. This is the basic logic that we assume that the oscillators are placed at the edges of the slit. Theta by beta is equal to 1. Then I theta is equal to I naught, which is basically some constant to capital A into alpha whole square. Here it is not alpha, it is actually beta. And A is the amplitude of the wave. So C is some constant. So find maxima and minima. What we will do? We will do di by d alpha is equal to 0. Sorry, in my note, the beta is actually alpha. So it's the thing. And the solution is either sine beta is 0 or beta is equal to tan beta. T square I by T beta square is positive when sine beta is equal to 0, and it is negative when this is beta is equal to tan beta. So this will give minima from the calculus, and this is going to give us the maximum. So first discuss the condition of minimum. So sine beta is equal to 0, that means beta is equal to m by m here plus minus 1 plus minus 2 plus minus 3 and all. So that means d sine theta is equal to m lambda. So they are the value of the minimum. So for simplicity, we can make it b small b. Then this is also b small b. So b sin theta is equal to n lambda. That is basically a condition for minimum. Here m is when m is equal to 0, that is not minima, that is basically a maximum. This is principal maximum. Because at m is equal to 0, sine beta by beta is equal to 1. Okay, the maximum. So from beta is equal to tan beta, we get that one value of at beta is equal to 0, that will happen. Another values are plus minus 3 pi by 2, plus minus 5 pi by 2, and so on and so forth. So from this relation, we get to know that another will be plus minus 7 pi by 2 and so on and so forth, where this relation beta is equal to tan beta will be fulfilled. So the intensity of the first of principal maxima would be I is equal to psi limit eta tends to 0 I naught sine square beta by beta square, which is equal to I naught. The first secondary maximum. Let's say it's I1 is equal to I naught sine square 3 pi by 2 by 3 pi by 2 whole square. And that would be 4 by 9 pi square I naught. And the intensity of the second maxima is I2 is I naught sine square 5 pi by 2 by 5 pi by 2 whole square, which is 4 by 25 pi square I naught. The secondary maxima are very feeble compared to the principal maxima, and their intensities diminish very rapidly with the increase in order number. From this, we get to know the intensity of secondary diminish very rapidly. The increase in order number. So the intensity becomes like this. So the peak would be here. Then they will diminish like this and the same. So this peak and this peak, they are I1. This is I0, this is I2. This happened around 3 pi by 2, almost at 3 pi by 2, not equal to 3 pi by 2. It's 2 pi, this is 3 pi. These are because of the arrangement and all those things, optical arrangement. So for first maxima, for first minima, we know that b sine theta is equal to m lambda. Okay. So for very small angle, basically this is b theta is equal to m lambda. So theta is m lambda by b. For n is equal to 1, theta is lambda by b. So this is basically first theta position is set on either side. So the angular width of the principal maxima would be 2 theta. So 2 theta is 2 like L lambda by b. And when there is white light, the condition of minima of rays incident normally on the slate at sin beta b sin theta is equal to n lambda. So it depends on lambda. So lambda r is greater than lambda v. So theta r will be greater than theta v if white light is employed. Theta r will be theta v. Central maxima will be white. But other maxima would be colored. Red maxima will be further violet. Now we go to double slit. Okay. So for double slit, I is equal to I naught. This is 4 square beta by beta square whole square with 2. A is the distance between the slits. So here it matches, but in the class slice it was written D. So this is the I. So when theta is equal to 0, I naught is equal to 4I. This is the maximum, or we can say principal maximum. When Kp is less than 1, sine beta by beta becomes 1. And the equation reduced to flux density expression for long line source goes to the slit experiment plot. If alpha is equal to 0, I theta is 4I naught sine square beta by beta square. And this is single slit expression. So condition for minimum A sine is sine square beta by beta becomes 0. So that means the sine beta needs to be 0, but beta cannot be 0. Therefore, beta needs to end by, and n is equal to plus minus 1, plus minus 2, and so on and so forth. So B sine theta is equal to m lambda. And this condition is called diffraction minimum. And due to interference pattern of two slit of diffraction pattern, we will get an interference minimum also. So cos square alpha when it became 0, then also we get this. That means when A plus B sine theta is equal to 2s plus 1 lambda by 2, we will get also the minima. They are called interference minima. And the condition of maxima, then again, one condition would be, this is one condition of minimum, this is second condition of minimum. One condition would be sine square alpha by alpha square is going to 1. So that would happen at alpha is equal to 0 and plus minus 3 pi by 2, plus minus 5 pi by 2, and etc. And another condition is a plus b sine theta is equal to p lambda, where p is equal to 0 plus minus 1 plus minus 2 and so on and so forth. So now we know the condition for 2 maximums and 2 minimums. So what happened that cos square pattern is basically this cos square alpha. This pattern is cos square alpha. And suppose this is diffraction pattern. So this is sine square beta by beta, and this pattern is multiple of 2. So what will we get? We'll get an envelope. We will get like this. Then and so on. So here you can see there is a pattern here. This is this, basically this. This, sorry, for simplicity, you can have. So this pattern is a principal maximum here. This will be there. This will be there. This will be missed here. So this here, this function is giving you the maxima, but diffraction pattern is not giving you the maxima. It's 0 here. So in general, you will get 0. So that's the missing order. And which order will be missed? That is basically a plus b by b, which is equal to p by m. So if a plus b by b is equal to 2 by 1, then b is equal to 2m. So that means 2 4 6th order interference maxima is absent. Which is basically due to first, second, and third order of diffraction. So, fraction minimum. So this is a two-slit diffraction pattern. So when A is equal to 2.5 and B is equal to 0.75, you see that there is a missing order of third. Okay. So when A is same, B is being reduced, you can see that the central lobe is become more and more right. So you see here first, second, third, then there is a like off. Here first, second, third, fourth, fifth, then there is off. Then first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, then off. Because A is 10 times of B here. So there is a different calculation. Can see that A plus B sin theta is equal to that. So when A is equal to MB, M is any number. In B, then there will be two fringes within central diffraction peak. Now we will go to multiple slit diffraction pattern. That is basically I theta is equal to I naught sine theta by theta whole square into sine, so n alpha by sine alpha whole square. So again, at as theta is equal to 0, we get the principal maximum. So then I not we scroll up. So the result of intensity depend on this factor and this factor. So for maximum, we get alpha is equal to n5, n is equal to 0, plus minus 1, plus minus 2, so forth. This is principal maximum. So secondary maximum, secondary maximums will get n out of n alpha is equal to what alpha, which is alpha is equal to n. No, this is not alpha is equal to n. Right? These values will give the secondary maximum, but at the values of that, when alpha gets to n5, then it is principal maximum. And for secondary minima, this is basically alpha is equal to plus minus 3 pi by 2n plus minus 5 pi by 2n, so on, so forth. This is the for secondary minimum. alpha is equal to plus minus pi by n plus pi minus 2 pi by n minus 3 pi by n, so on and so forth. This is the multiple slit diffraction pattern, and the pattern will be like this. So minima then again maxima then. And this height and this height will not match. They will actually drastically reduce the part. Like this. And this part is sine beta by beta whole square. There sine n alpha by sine alpha whole square. Now we discuss some question. So let's dive into some question. In this question, the question is, in this arrangement where a large lens L2 is close, narrow, point 0.25 millimeter slit in the aperture screen. The illumination is green magnesium light at Pashwa 18.36 nanometer. Determine the width of central maximum formed by L2, which has a focal length of 65 centimeters on the viewing screen sigma. So here the width of the principal maxima is so here we need to draw a line from the center of L2 from the central axis at an angle theta out to the point on sigma. So there we need to draw a line. Okay. So image form at sigma is perpendicular to the focal length f. Let y1 be the distance on sigma from the central axis to first irradiance 0 at B. So this is y1. So the width of the principal maxima, then 2y1. There is a first irradiance 0. Zero at B. Then the width of the principal maximum here is 2y1. Here tan theta 1 is y1 by f. So y1 will be f tan theta 1. So this distance is basically f. This is theta. It is theta 1 for things. F tan theta 1. For small value of theta 1, that became y1 f tan theta 1 is equal to f sin theta 1. And we know b sin theta equal to m lambda. So y1 becomes f lambda by b. So now putting all 2y1 would be 2 into f by lambda by b. Putting all this value, we get 2.695 millimeter. And so the width of the central maxima is this. Question 2. Imagine two narrow parallel long slit, each V wide, separated by A, which is 0.100 millimeter. These are illuminated perpendicularly perpendicularly by plane waves of yellow sodium light. Lambda is equal to 589.6 nanometer. The resulting fringe pattern on distant screen consists of a total of nine narrow maxima. That gradually decrease in brightness on either side of the central peak. Determine the approximate slit width V. See, for single slit diffraction, we know B sine theta is equal to m lambda. And for two slit interference, that is A sine theta is equal to m lambda. So this is MD, this is I, this is D, this is I. So I said, since there are 9 maxima, there must be 4 subsidiary peak on each side of the central peak. And hence Mi is equal to then mi is equal to plus minus 4. So here when I say that when A is equal to n be 2n fringes, that means 2n plus 1 fringes actually. So sine theta 4i equal to sine theta 1t. So the diffraction maximum, diffraction minimum. First diffraction minimum. So theta so sine 1 theta t is equal to theta 4i. So 4 lambda by a is equal to lambda by b. So 4b is equal to a. So b is basically 0.1004 by millimeter. So that is b is equal to 0.025 millimeter. So the central diffraction maxima, the location of central diffraction maxima is equal to location of 4 interference maxima. So that's why we can write this equation. Imagine 12 narrow parallel long slits. Each be millimeters wide. It's separated from parallel long slits. Each be millimeters wide is separated from the next slit by a center to center distance of Use a form of verb reflection pattern on a distant screen. Determine the relative irradiance with the first order principal maximum. Information compared to the zeroth order principal maximum. So basically, there are 12 narrow parallel long A slates which are b millimeter wide, and that if A is equal 5b, the apparatus is illuminated by a plane wave and produce a form of a diffraction. So we need to determine the relative irradiance of the first order principal maximum compared to the zeroth order principal maximum. So principal maxima occur when sine n alpha by sine alpha is equal to n. So only this term survives. So A is equal to 5b here. So beta is equal to pi lambda b sine theta is equal to pi lambda by A by 5 sine theta, which is basically alpha by 5. First order maximum occurs when alpha is equal to 5. That means beta is equal to pi by 5. So for m is equal to 1, I theta is equal to I naught sine beta by beta whole square. I naught is equal sine pi by 5 by pi by 5 whole square. So I theta by I naught is equal to So I naught also has n square. So that's being said, we don't need to write n square separately. So here it would be sine pi by 5 by pi by 5 whole square is equal to 0.5878 0.6283 whole square, which is 0.936 whole square. So that is 0.8710. So the first order principal maxima is is 0.87 times as large as 0th order maximum. Now move on to the next question, question 4. Question 4, which is one of the question of one of the question of the quiz. Two beams of wavelengths 800 nanometer and 1550 nanometer are incident on the same narrow slit, which has the smaller Fresnel region. So lambda 1 is 800 nanometer, lambda 2 is 12, 1550 nanometer. So we know that R needs to be less than p square by lambda. So we can consider this is the Fresnel range. So p square lambda 1 is greater than b square lambda 2 because lambda 2 is greater than lambda 1. Okay. As lambda 2 is greater than lambda 1, 1 by lambda 2 is less than 1 by lambda 1. So b square lambda 1 is greater than b square lambda. So 1550, which is lambda 2 nanometer beam, has the smaller region. Question number 5. Slit of plate A 0.2 millimeter is illuminated by light of wavelength lambda is equal to 550 nanometers. Find the angle corresponding to first minimum. So we know for single slit minimum condition is A sin theta is equal to m lambda. For first minima, m is equal to 1 plus 1. So A is equal to 0.2 millimeter, which is 2 into 10 to the power minus 4 meter. Lambda is equal to 530 nanometers, which is 5 into 3 into 10 to the power minus 7 meter. So sine theta, from here I have shown you earlier, sine theta becomes m lambda by a. In that scenario, sine theta became lambda by a. And for small angle, this is equal to theta. So that is lambda by a. That is 5.3 into 10 to the power minus 7, 2 into 10 to the power minus 4. That is equal to 2.65 into minus 3 direct. So that is equal to 0.152 degree. This is the result. Rest of the question of the quiz, previous year quiz, are the basically theoretical question that which model explains diffraction. That is wave model. What is this Huygens principle limitation? So diffraction is a limitation. That's why we need Fresnel's Huygens-Fresnel's principle, which is the combination of Huygens and Fresnel's. Then effect of having single slit width. So if there is a single slit width is reduced to a half its initial value, say if a single slit width is reduced half its initial value, what happens to the diffraction pattern? So we know A sine theta is equal to m lambda single slit minimum. So theta is equal to m lambda by A for first minima. M is equal to 1 lambda by A. So central maxima width is basically 2 theta. That is 2 lambda by A. So if A dash is equal to A by 2, then theta 2 theta dash is equal to 4 lambda by A. So the deflection pattern becomes wider. So that's how I need to think. That is for today. Class.